For introduction to nanochemistry, today we're going to talk about the metallic nanoparticles, which is one of the very favorite nanoparticles applied in many fields. The characters of metallic nanoparticles, uh, there are many actually. First of all, the nano-sized metals with dimensions within the size range from 1 to 100 nanometers or sometimes higher to about 500 nanometers are called metallic nanoparticles. And because of the size of nanoparticles, everything is changed and differs from the bulk material. Um, for example, if we look at the energy level, for single atom, as you know, that we have atomic orbitals, right? So when they combined to be dimer, trimer, or into cluster, then the atomic orbitals combined and mixed together, constructing a molecular orbitals. So into a nanometer scale, nanoparticles with somehow less than several tens or hundreds nanometer, the energy level still be in discrete or quantized levels. But if the particles are mixed together, combined together, then at the very end we have a bulk material with the energy levels are blended together and then constructing the band in state like S band and P band and everything. So nanoparticles, clusters, the energy levels are very different from the bulk material, from the bulk metal. That means the excitation energy of electrons and electronic properties of this kind of small uh, little things are very different from the bulk material or the bulk metal. Apart from that, the surface energy is quite high comparing with the bulk metal. As you can see, for example, in the nanoparticles showing here in the picture, we have kind of edge or surface or faces, um, so many faces. So comparing with the volume, right? So we have very high surface area, and it leads to the high surface energy because the lack of chemical bonding up here, right? So they are unbalanced, and yeah, they have high surface energy. So somehow they have to stabilize by absorption of some atom molecules on top of the surface. This is another character of the nanometal. A very important property of nanometal is the surface plasmon resonance. Surface plasmon resonance is the oscillation of electron clouds in response to the electromagnetic field that is travel past by. So the black sphere here is the metal. And yes, of course, we have electron clouds of the metal, which can bounce up and down according to the electromagnetic radiation. So if we have a electromagnetic radiation with a certain wavelength or certain frequency, the electronic fields can then interact with the electron cloud, which is negative charge. So as you can see, the bouncing of the electron clouds here is corresponding with the electromagnetic field. So the bouncing of electrons depends on so many things and can be described actually by an equation which is called Means theory. So it depends on shape, size, and type of the metals. So each particular particles have a specific frequency of electron resonance. So if it is activated by the electronic field of a certain electromagnetic radiation, we can then have this kind of resonance, which is called surface plasmon resonance. And hence, our metal nanoparticle can have characteristic color based on this surface plasmon resonance. One of the very good example of this kind of properties is the what you call the stained glasses. So the stained glasses from the medieval period is very permanent and very withstand with the weather, climate, and everything, because these colors are not from the organic dyes, and it is very difficult to be oxidized and faded away over time. Because actually, these are from the metallic nanoparticle. For example, the red color here is the characteristic color of the gold nanoparticles. So, within the nanosecond size, spherical gold, they have a kind of frequency of the electron cloud bouncing, which is resonated with the wavelength of the electromagnetic radiation at about 500 something nanometer, and hence it can exhibit the red color here. And again, yellow color over here, as you can see, is from silver nanoparticles. So all these colors are from the metal nanoparticles that is mixed into the glass. And this is how our stained glass can exhibit colors. So those are a specific character of the metal nanoparticles. So the metal nanoparticles can be achieved, can be synthesized by many kind of methods. Yeah, some of the methods is very popular. Some of the methods are quite difficult and complicated. Anyway, the synthesis method can be divided into two major types. The first one is called chemical methods, and the second one is called the physical methods. Yes, of course, we using chemicals and using kind of physical mechanic in order to synthesis the metal nanoparticle. The chemical methods, there are plenty of them actually. For example, we have metal ion reduction, starting from metal ion, and we have kind of chemical reaction to reduce the metal ion into the metal with the oxidation number equal to 0, the metal. Or we can also synthesize using microemulsions. So instead of solution or aqueous media, we can make kind of emulsion, micelles, thing like that, to trap the metal ion inside and then reduce it in the microemulsion form. We can also, using thermal decomposition of the metal or electrochemical methods in order to reduce the metal ion. So there are many methods can be achieved. For physical methods, there are plenty of them again. For example, the plasma reduction, microwave reduction, laser ablation, gamma radiation. So we use this kind of energy, electromagnetic radiation, things like that, in order to synthesis the metal nanoparticles. So many types, many methods to prepare the metal nanoparticle. So I'm gonna give you some kind of examples to give you some ideas how we can create this kind of little guys, metal nanoparticles. I would start with a very popular method like the chemical reduction. So chemical reduction for gold nanoparticles is very well established because first of all, the gold is very inert, it's very stable. So to develop the synthesis pathway for gold nanoparticle is quite easy comparing with other active metals like iron, copper, things like that. So gold nanoparticle is easier to start with. And first reported um, synthesis method is published by Michael Faraday many more than 100 years ago. And then the guy who we normally cited his uh, synthesis method as our reference for synthesis of gold nanoparticles is this guy, the Tekevich. He started from the tetraoral auric acid, but sometimes some procedure using tetrachloro aurate ion. They are the complex, tetrahedral complex of the aurum of the gold, and then reduce it. So the reduction method can be varied using different kind of metal salt and also different kind of the reducing agent. But this sodium citrate is very popular here because sodium citrate is not really uh, reactive, so it's quite stable and controllable comparing with like sodium borohydride or something stronger than that, which is very difficult to handle, very difficult to control. So sodium citrate is a very good choice, and we normally use it for the gold nanoparticles. So after mix them up together, the citrate ion can reduce our gold. As you can see from the structure here, the gold is in uh, 3 plus oxidation state, plus 3 oxidation state. So from plus 3, we're going to reduce it to be 0. And then by metallic bonding, they're going to attach, stick together, and then we have gold nanoparticles as a result. The picture showing here on the left hand is a characteristic yellow color solution of the gold 3. And the right hand, the red color here, is the gold nanoparticles. So it's similar to the color of the stained glass I have shown you before. And if we use the laser beam pass through our solution, as you can see, by naked eye we may thought that these two tubes contains clear solution, but actually by Tyndall effect this can confirm that the yellow solution is the solution. But for the red side on the right hand, as you can see, we can observe the Tyndall effect. So that means the particles inside is in nanometer scale. So they reflect the light and have this kind of Tyndall effect. And on the right hand red color is the characteristic red color of the spherical gold nanoparticles. So the synthesis is very easy, very simple. Just mix them up together, heat to about 80 degrees Celsius for half an hour sometimes, or less than hours, and then at the end we have this kind of red color solution. From TEM image, as you can see, we can see the little dots, circular dots here, and these are gold nanoparticles synthesized from the Turkevich method. And if we zoom into the picture a bit more, we can see that our spherical gold is about 9 nanometer. This is actually from my lab. And the red color, if we use the solution and observed by UV visible spectroscopy, as we can see, this is the characteristic red color absorption. So the absorption maxima is about 520 nanometer. The very advantages of this chemical method is the economy friendly, because the chemicals are quite cheap, and the instrumental is very simple. We can starting from a bigger and just that, right? A bigger and with heating hot plate, stir it, and that's it. So it's quite simple, easy, and very cheap. Next method. Oh, no, this method. I want to go deeper in detail about the mechanisms a bit. So from firstly, our metal ion. So actually this method is not using for just gold nanoparticles. We can use it to synthesis like silver nanoparticle or many other metal nanoparticles starting from the metal ion with a proper reducing agent. So it actually depends on the reduction potential of the things, right? So starting from metal ion, we just reduce it to be metal, right, by chemical reduction. So the metal here can then attach with the next metal ion, reduce it again, and be a dimer like this. Or from the metal atom, right, several metal atoms can attach to each other using the metallic bonding, right? So they grow up, right? So from this is called nucleation step, right? They're growing up, and the very first stable cluster is this one, right? And this is irreversible process now. This is very stable cluster. As you can see, we have in total 13 atoms, right? With A, B, A, A, B, A, B, hexagonal closest packing style. So as you can see, we have hexagon at the B layer. Actually, we have a central atom inside. And then on top of it, we have layer A, triangle, right? And at the bottom layer, third layer, we have also this triangle. So this is ABA, or maybe ABC, closest packing style. And this is the very first stable cluster of the metal. So after you have this one, then they grow up again using both pathway, right? So sometimes the cluster uh, crash with themselves, right? And then growing up. So this is the growth step, right? And yeah, from the small cluster combined with small cluster, we call the second growth. But if we starting from this one and growing from this, we call it as primary growth. But anyway, because metallic bonding is very strong, so if we doing nothing, they're gonna end up with a chunk or bulk metal at the very end. So what we have to do is to stop it from growing up forever. To stop it, we have to stabilize our nanoparticles with something. In the first picture on top, we stabilized it with some kind of long chain hydrocarbon maybe, or maybe we stabilized it with a huge molecules like polymer. So if we have polymer absorbed onto the surface of the nanoparticle, which is very easy actually, because as I said, that the nanoparticles has very high surface energy, right? So we have to stabilize it. So it very have high affinity absorbing organic molecules on top of the nanoparticles. So with the steric effect, they inhibit the the kind of metallic bonding between clusters, right? And we can stop the growth mechanism at the end. Another way we can do is stop it by the electronic field. So if our nanoparticles is absorbed on top with some kind of ion, for example, citrate ion, as I mentioned earlier in the synthesis step, gold nanoparticle synthesized with a citrate ion. The citrate ion can have the affinity on the surface of the gold nanoparticles. So if our citrate excess amount of the citrate ion absorbed onto the surface of the gold nanoparticles, so at the end our surface of the nanoparticles contain negative charge. So we have negative and negative charge, right? So there are electrostatic repulsion among the nanoparticles, and then we can stop the growth, the secondary growth of the nanoparticles by stabilization of the anion, cation, or polymer, right? Using electrostatic or using steric effects. Another method that is very kind of popular among the chemical methods is the microemulsion. So in microemulsion, we have to prepare the emulsion of the metal ion and also the reducing agent. So normally the emulsion, microemulsion, we have to use kind of two phases, right? Non-polar and polar solvent. The polar solvent dissolved our metal and reducing agent, for example, hydrazine, for example, citrate. Right? So with water, hydrazine, or citrate ion, or any other kinds of sodium borohydride of the reducing agent can be dissolved into water, and also for our metal ion. But then again, we mixed our aqueous system with organic system. So using kind of surfactants, we creating the reverse micelles. So as you can see, all of our aqueous doublets of metal ion and reducing agent is now stabilized by the surfactant molecules, and they can now stay in the organic phase. So after that, we mixed our metal ion and the reducing agent in microemulsions together. So then these particles can have emulsion exchange. So two of the reverse micelles can fuse together, and then by fusing of the reverse micelles, reducing agent and metal ion can can mix with each other, and the chemical reaction happens here in the reverse micelles. So after reduction, we have our nanoparticles, metal nanoparticles, stay here inside the microemulsion. And after we have nano um, metal nanoparticles, we can then like calcine, get rid of the surfactants, or doing further surface modification. For example, if we put kind of silica source, thios, everything, we can then cap our metal nanoparticle with the kind of glass silicon oxide. So we can modify the metal nanoparticles, surface of metal nanoparticles with something else. So many things actually. So this is microemulsion. The very good advantage of the microemulsion is you can prepare a quite uniform size distribution of the nanoparticles by controlling the size of microemulsion, the size of the reverse micelles, using the concentrations, using type of solvent, and also the surfactant molecules. So we can control the size of the emulsion, the size of the reverse micelles, and hence we can control the size of metal nanoparticle inside. Another chemical method that I want to mention here is the electrochemical method. So the electrochemical synthesis, we use the two electrodes, oxidation, reduction, and then we put the metal ion inside and then reduce it. Okay. So on the anode side, we have our metal, right, the target metal, and then the cathode. It can be anything. Normally we use platinum cathode. Okay. So in the beaker, we can put the metal ion and also the stabilizers if I want. And then with the magnetic stirring bar, we can then start our reactions. So what happened here is that we have two electrodes, anode for oxidation and cathode for reduction. So the metal in the anode can be oxidized, okay, to be M plus, which is the same thing here, metal ion dissolved into our beaker, into our solution. So after that, we have M plus. The M plus go to the cathode, right? So the cathode reduction, right? So our M plus is reduced at the cathode and turn out to be M0. So by metallic bonding, we can then have the metal nanoparticles from this kind of synthesis. Anyway, in our solution, we normally mixed stabilizer into the solution media. So the stabilizer can stabilize the metal nanoparticles by a steric effect, or maybe by the electronic effect, electrostatic repulsion. It depends on the stabilizer you are using. So at the end, we have stabilized metal nanoparticles. Okay. So these are chemical methods. The very important thing here, the advantage of the electrochemical method, it is quite eco-friendly because we don't have to use a very strong reducing agent, so we just get rid of reducing agent. So instead, we use electricity, right, to reduce the M plus. So in order to reduce it with hydride, with citrate, with anything, we use electrons to reduce it from the cathode. Okay, so we can use less amount of chemicals. That means we can cut off the uh, excess amount of waste, right? So treatment is easier, and we have pure metal nanoparticles at the end. Now we are going to look at some of the physical methods, and the first kind, first of its kind, I want to show you the microwave plasma. The microwave plasma is using kind of microwave, creating a plasma of very hot gas. So in this kind of thing, we have to use a precursor, which is our metal salt, maybe. Like if we want to make a copper nanoparticle powder, we're going to starting from copper carbonate, copper sulfate, thing like that. So from powder of these metal salts, we can then flush into our reactor. So in a carrier gas, they can transfer our powder of the metal salt into the microwave plasma. So microwave plasma can then uh, disintegrate the metal ion and the anion, separate them apart from each other. And with this kind of hot plasma of electrons, then we can constructing the metal uh, zero oxidation state, and then they gonna bind together to be nanoparticles. So after we have nanoparticles, it is then filtered and then collected into a new chamber. So this is a microwave plasma. A very good thing for this method is we can prepare the metal nanoparticles in very fast rate without solvent. So if we want to make a nanoparticle without capping agent in the solid powder state, we have to use this microwave plasma. But as you can see, we have to prepare the instrumentation quite sophisticated, right? Comparing with the chemical method. Physical method like microwave plasma, you have to have kind of instruments and setup with proper setup to synthesis. Another very popular thing for physical methods is the laser ablation. So for laser ablation, a good thing is uh, we have no the stabilizer is really don't necessary in the system. Starting from solid target, the metal itself. Okay, we may put the metal solids in a solution, right? Composed of solvent, metal ion, and maybe some additives if you want the stabilizer. But if you don't want the stabilizer, you don't have to put it in. And then we have a laser focusing down into onto the surface of the solid target. So they are kind of micro explosion. So yeah, it's the explosion on the surface. So metal and everything is disintegrated from the solid target. So with the laser, they have kind of metal ion, electron, and water can be dissociated using this laser as well. And somehow the reduction happens over here, and at the end we have nanostructures or nanometal here in the solution. So this is another physical method, right? No stabilizer required again. So without stabilizer, we can easily modify the surface of the nanoparticle. So this is a good or advantage of the physical method.